All right. Quick announcements. Nothing due this week, but we have our first part of our project due next week. Then there will be a part 2 to that that is going to be implementing the graph search algorithms that we have studied into that. So again, it's broken down into 2 parts, kind of the data structures portion of the assignment, making the actual structure, and then we're going to build in the algorithmic support for it in the next assignment. One important part of this is that you do not have the JSON specifications that you need in order to actually import and read a file. So that is coming today. Hopefully, I let the grader know that we need to talk about this and we need to be on the same page about it because his grading scripts need to be able to parse that input. So I know some of you are getting started on that. And if you're in that situation, my recommendation is to start the adjacency list and adjacency matrix classes because they don't need to read from a file in order to be tested. You can write a tester for that just creates a graph in line and make sure that you're able to add to them, to delete from them, to get from them. So start with those couple classes, and by the time you're done with that, hopefully we have released the JSON specifications. If you're thinking about what that might look like, if you want to try it out, we're planning to have a list of all of the vertices before all of the edges. Exactly what that looks like, I don't quite know yet. There are still a couple different ways we could implement that, but if you wanted to start building in some logic, that's the order in which they'll appear in the JSON. See, other than that, we're working on getting sequence alignment back to you over the next couple of days, and exams are in the other graders to-do list now. I've handed them over, so we should expect hopefully to have those I requested by the end of the week. I'd like to go over them on Friday, but I will hopefully have a little bit more information for you over the next day or two if that is going to be the case. Questions or concerns on course logistics before we dive back into what we were talking about last time? Flow networks. Okay, so last time we were talking about flow networks and we found that there's a smudge on the board. We found that we could not handle this concept of anti-parallel edges, and we made up for this by making an extra vertex. I like to call it a ghost town, something that we ship them somewhere, and it's really just you're shipping it from V1 to V2, but there's an arbitrary stop, not stop along the way, and it just lets us visualize this in a graph form and allow for those anti-parallel edges. And we'll see why that is the case when we come up with an actual algorithm for solving the flow network. We'll see why we need that edge in reverse while we solve the problem. So we're not just saying we can't have this arbitrarily. It becomes something that we need to be able to represent the problem when we go to solve it. So of course, flow networks can also have multiple sources or multiple sinks. This makes sense. A large company might not just have one puck manufacturing plants. They might have multiple in different places. And there may be multiple locations, warehouses where they are stored, or retail locations where they are sold. The question I have for people is, what does adding multiple sources or multiple sinks do to the problem? How do we change how we think about the problem if that is the case?
Figuring out the output based on like a single location, or figure it out for locations throughout the whole graph.
Yeah. So there will be multiple possible places that can be producing, multiple possible places where it can be distributing, but there's still going to be some constraint on the maximum amount that is produced. Does it matter where in the network the production happens? If there are multiple sources, does it matter which source we produce at? If we produce 100% of them at one source instead of another source, or spread them evenly? If there are three, one third, one third, one third.
Yeah, so how the data flows through.
Yeah, it depends on if it's connected. Do each of those sources connect to each of the sinks in some capacity? If yes, then great, it's a trivial problem. If not, then what we really have are separate flow networks, which we can solve sequentially. So regardless of how we set this up, it ends up being a trivial solution. It's trivial to add sources and sinks to the problem. So here's one other way to consider it. Here's a problem with multiple sources and multiple sinks. It turns out we can trivialize all of this and change how we view this problem with one simple change. And that is backtracking the source to a new ghost town and forwarding the sinks to a new ghost town. And now we have a single source, single sink flow network with infinite capacity between the one source and the three real sources and the two real sinks and the one sink. That's exactly the same problem. However, now it's the single source, single sink flow network problem. So we never have to worry about this problem scaling because it has an absolutely trivial solution, which is really cool to think about. So if we just move forward focusing on the single source, single sink problem, it will also solve the multi-source, multi-sink problem. So let's take a look at one general method for solving flow networks. This is called the Ford-Fulkerson method. And all we're going to do is, I hinted at this, I think, in the last class, but we're going to find what we're going to call an augmenting path, which is just a simple path from source to sink that has at least some flow available in the flow network. The edges of that just indicate we can update to increase the resulting flow. We start with no flow from source to sink. We find an augmenting path. That's just a simple path between source and sink. We're going to find the bottleneck for that augmenting path, and we're going to increase the flow of the network by that bottleneck, and then decrease the allowable flow from each of those edges on that augmenting path by the amount of flow that was the bottleneck. We just iteratively do this. We're going to continue to look at and find augmenting path after augmenting path after augmenting path until there is no simple path from source to sink anymore. As soon as we don't have that simple path, that means that we've maximized the flow in the network. And that is a fairly straightforward algorithm. In fact, this entire process is relatively straightforward, which is why it's so cool. We'll find the one big issue with it in a second, but that is the case. So the residual network from this takes in a flow network and a flow, and the residual network consists of the edges representing how flow can change on the associated edge. This just means how much extra flow can we handle on that edge. So for this, we actually utilize the concept of that anti-parallel edge. Basically, we're going to have a capacity flowing from source to destination, and we're going to have an amount of that capacity that is being used flowing in the opposite direction. Think of it like adding and subtracting. If you have plus 10 minus 8, the equivalent is plus 2, but you can represent it as an expression, some of which is forward flowing, some of which is backward flowing. If the forward flowing is the amount of flow that can happen, and the backwards flow is the amount that is actually happening, the result in the direction of source to destination is the amount of extra flow that we can handle. All right. So we're going to convert this network into a residual network, where now the forward edges represent our unused flow and the backward edges represent the existing flow in that direction. So it ends up looking like this. And the way we're going to read this, I want to replace this pen anyway. We'll see how much ink it has. This says that there is 11 tons of material flowing from source to V1, and there is 5 remaining tons of capacity that could flow from source to V1. It's a little bit counterintuitive that the backwards edge is telling us how much is flowing in the source to V1 direction. But that's what we have here. The edge in that direction is how much more flow we can add to that in order to maximize the capacity, maximize the flow based on the capacity. Any questions on this idea? Or why or how we're representing it the way that we are?
I guess I'm confused how V1 knows the send source of the bin.
Yeah, this would have been a middle point in this method, which we needed in order to represent this. But we can look for any simple path. The fact that a simple path exists between source and destination now tells us that we can increase the flow along that simple path by the bottleneck here, which is the 4. So we have a way of iterating now and seeing, is there a simple path? If there is a simple path, then what we do is we end up canceling, like this 5 backwards becomes a 9, and there is no edge going in this direction now. And so there is no simple path anymore through V2 to V3, that edge. On the other hand, there is, that's it. There's no other way to get to T. It looks like we are blocked now. So that becomes a way of knowing termination when you can no longer find a simple path from source to sink. And we can analyze how much flow is happening by just looking at the combination of all of the edges that come into T. This eventual 15 plus 4, I guess this would also become a 9, would become 24. And you just have to look at the material that is flowing into the sink to know how much is being produced. You can also look at the sum of how much is being produced out of the source, and that should also be the same amount. So you don't need to do a complex analysis of the entire flow network to figure out how much material is flowing, how much is coming into the sink, how much is coming out of the source. Either one of those will answer your question. And it becomes a very nice representation. Question remotely. Can't see the vertex names. Let's zoom in a little bit so you can see the vertex names. So this 12 of V3 connecting to V1 means that it flows left to right. Yeah, there's a flow from V1 to V3 with capacity 12. And all of that flow is in use. So it flows left to right. If there were an edge from V1 to V3, this would be an unused capacity. There'd be the ability to send more flow between V1 and V3. The 12 tells us how much flow is going between V1 and V3, and the fact that there's no edge from V1 to V3 says there's no further capacity that we can use. Does that make sense to everyone?
I suppose so.
Then we call the augmenting path here the simple path from source to sink. Each edge has a positive value. Then we can find the actual residual network from the bottleneck from that augmenting path, loop that as long as there is an augmenting path, and we terminate when we can no longer find a simple path from source to sink. This network converges immediately, which is nice, because it's already partially underway. But we'll see that that's not necessarily the case eventually. So this is what it looks like after we use the augmenting path, and we see that there is in fact no further path left there. We can't come up with a simple path that gets us to the sink. If there were a possible path, we would continue to iterate. How would we represent it if we wanted to show the flow from V3 to V1 with capacity 12, but none is being used? It's exactly the same, and it turns out to be exactly the same idea. So we would still have that arrow from V3 to V1. Sorry, it'd be V1 to V3 if it's capacity from V3 to V1. But we would see that it's, instead of 12 out of 12, we would see it's 0 out of 12. So you can either represent it as a hard-coded number or a fraction that is the amount of material being used. It's a good question. So since there's no augmenting path in image D, we would terminate. So let's take a look at some pseudocode. Here's Ford Fulkerson. The question that I have for you: what is the bottleneck of the runtime? Where is the runtime of this coming from?
See. Wow. 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 Whew.
Any thoughts? Yeah.
I would assume the bottleneck will run or within the while when you're checking for each edge. So if it's a dense graph, that's gonna be pretty high value.
Sure. Yeah, when we're iterating over each edge, we can just automatically assume dense graph
Yeah.
in a worst case. Sub-question: what is the process for finding the augmenting path?
Mine's the B, so. Well.
Yeah,
Would be kind of like a
we could use some kind of depth first search.
Yeah. Maybe.
We would want to bias this in some capacity. So a depth first search can get, as long as we don't handle it, stuck in a loop where it's kind of, if a loop exists,
Oh, it's actually.
we could make sure that we don't go back to a vertex that we've seen before. Is there any value in minimizing the number of edges in the shortest path or in the flow from source to sink? If there's an augmenting path, finding the shortest by edge number of edges, which would tell us to use breadth first search rather than depth first search.
Yeah, that's exactly what I was thinking.
But is there value to that? Kind of depends. What is the actual variable that matters here that's going to keep this either as efficient or not efficient?
Weights of the graph.
Yeah, when we think of the bottleneck of a particular path that we find, if it is a low bottleneck comparatively, then it's going to be more iterations before we terminate. If we can find the highest bottleneck, maybe that kind of greedy assumption would allow us some way of minimizing the number of iterations before it converges. That would depend on how difficult the problem is to find the best path, the highest weight path.
Okay.
Is there any way to do that in an interesting way? This is actually a question that we will answer in the next unit, which is interesting. I can spoil it a little bit. We use Dijkstra's to find the shortest path, but we're not really interested in the shortest path, we're interested in the longest path by edge weight from source to sink. We could invert them and make all of the edges negative, but Dijkstra's doesn't handle negative edge weights.
No.
It turns out finding the longest edge path between a source and a destination is intractable. The shortest path is efficient and easy to answer. The longest path is best case exponential complexity. In fact, it's an NP complete problem. We can't even prove that it's best case exponential complexity, but we can tie it to other problems that are the best we can do right now is exponential complexity, to where if we could solve one of them, we could solve all of them. And that's what we're going to be talking about next. But the longest path problem is one of those problems. So it's very interesting that very related problems, one of them is easy to solve, one of them, as far as we know, is impossible to solve efficiently. We can still solve it, it just takes an exponential amount of time proportional to the number of vertices in the graph, which is wild. So, how should we handle this? Yeah.
Yeah, so I have a quick question about that. But not just, I assume, based on how you said that, it wouldn't be as simple as just changing it to looking at the greatest edge.
Yeah, because that would be a greedy solution where if your first edge is the greatest, is that part of the optimal solution?
Okay.
We don't know. We have to check the others as well, just to be sure. So it turns out that the way this is typically done is with breadth first search. It just minimizes the amount of time that it takes to find an augmenting path. If we go down depth first search, there's no guarantee of how many edges. We might, in the worst case, have to look at every possible edge based on how we break our ties with depth first search. So we find that breadth first search, in the average case, terminates faster. So we will use breadth first search, but it's not the end of the world if you chose to use depth first search here. But let's take a look at that worst case analysis. How many iterations of a loop are we running in the worst case? Let's go back and look at it. So the outer loop, how many times are we iterating that outer loop in the worst case?
10 times or well? No. Well, that's close.
Any guesses?
You're not very wrong. I don't know. Are you wait, sorry, which outer loop are you talking about?
A while on line 3.
Just that.
Yeah, how many times would that be run in the absolute worst case? If I could design the cruelest possible flow network for this code, what's the worst that I could do?
You mean exponential loop or
Based on some variable.
T?
It is not T. What is T? You're thinking of this being just that's the safe vertex.
I guess I'm having a hard time understanding what like, is this, it's just written in like a general length?
Yeah. Yeah. So it takes 3 parameters. Let's go through this and read it and make sure that we understand it. It takes a graph, a source vertex, and a destination vertex. then says for each edge that's going to be from vertex U to vertex V, and we just iterate each edge in the edges of the graph. Then we find the flow of that. We're going to set the initial flow to be 0 for each of those edges, saying that as we start the problem, there is no flow along that edge. While we can find that augmenting path in the residual network, then we're going to find the minimum possible value here between the edges that are in, let's see, what is P here? It's the parameter to this. Then
Yeah,
for each,
the path.
in the path, yeah. For each edge in that path, then we're going to update it by the minimum, this is just the bottleneck in that augmenting path. We're gonna find the bottleneck, and then we're going to update each edge by subtracting off that value and adding that much to the flow. So how much can go through is subtracted, how much is going through is added.
Okay.
And then we loop back around and find another augmenting path and continue to do that until we're done. And we return this object that represents the flow as we build the flow network, the flow graph from the original passed-in graph. Yep.
So would the runtime of that model would be the amount of vertices within the path
Interesting.
or any?
It's actually neither.
Oh,
This has nothing to do with the vertices or the edges in the graph.
not the graph, the path.
I can find the exact same path over and over and over and over and over and over and over again. And there's a way to do it. Let me show it to you. It actually is in big O of the amount of flow. Has nothing to do with the vertices, has nothing to do with the edges. In the absolute worst case, if the amount of flow between source and sink is maximum 10,000, then I could reasonably take 10,000 iterations of this in order for it to do that. So the challenge that I make for you is, can you draw out a network that actually takes that much time? We're going to spend a little bit of time doing this because I think this is a good exercise. Knowing this, knowing that in the absolute worst case, can you design such a network that is very difficult for Ford Fulkerson to solve? I have an example to show you, but I want you to think about it first. What would be necessary in the design for this to perform as bad as it possibly can? Yeah,
Could be like force and sinks could be hooks, a bunch of intermediary. Also that.
potentially, that's a good start. The issue is, if there are a bunch of small ones, then we would very quickly fill that flow and then have to terminate. You're on the right track. There is an aspect of something with a low flow threshold. But the trick is that we can't fill that low flow threshold and then call it a day.
No.
What happens if that low flow threshold changes direction and then becomes another augmenting path? And then changes direction and then becomes another augmenting path.
That type of thing would stack up, wouldn't it? 'Cause that. Things feels off. Oh, I'm missing. I have the right idea, I'm just missing stuff.
free to work in pairs, small groups, anything that makes sense here.
Pseudocode.
Like we're kind of stuck.
Yeah, we are.
Let's at least consider this. So the example that I have here is one that would be more trivially solved by breadth first search, but I could easily change this to not be trivially solved, to where this path is the best path.
Yeah.
So breadth first search would solve this very quickly, but you can imagine biasing this in such a way that, and when you write the code for this, you don't get to easily look for all of the possible paths that you could take. If this is a large graph, it's going to take exponential time to figure out.
Well,
Why would the meta one do?
Depending on how you break ties in your code. This is just an example. We could take these vertices and make very long paths, such that this path is really long, this path is really long, and then the best way, even by breadth first search, looks like going through here, and then looks like going through here, and then looks like we could force that. But the point is that this is a problem that we need to solve, because otherwise this is not efficient. And there is an easy way to solve this problem so that this never happens. But this is the worst kind of network that can exist if you are breaking ties arbitrarily. And this is also an important learning outcome for whenever you're implementing your own solution to something. If it ever seems like, I'll just break the tie in an arbitrary way, and how bad can it possibly be? This is an example of when breaking ties in a particular way really matters and can change the worst case behavior of your entire algorithm just off of the assumptions that you're making. This no unit test would break on this. It would still work. It would just take way longer than it needs to. And unless you are thinking about that in your design, you would find that your eventual solution is making a pretty poor decision. So just determining the maximum augmenting path is intractable. So this is not something that we can solve in an amount of time that is less than the entire Ford-Fulkerson model. It's a harder question to ask what is the longest augmenting path in a large graph than it is to run through this entire algorithm, even as suboptimal as it is. So we need something that helps us more intelligently pick an augmenting path. So Ford-Fulkerson is a generic method that involves the augmenting paths, the residual networks, this iteration, but the actual algorithm that is used in practice is one that uses a trick to pick an intelligent augmenting path so that we can get a better worst case guarantee on the termination of the algorithm. And even an algorithm that seems and is fairly trivial to implement, we find there to be ways that we can reduce the complexity of the result. And we find this a lot in algorithmic design, algorithm studies. We're gonna look at the Edmonds-Karp algorithm. So the trick is actually here to use breadth first search. What if we use the augmenting path with the fewest edges regardless of their edge weights? So this would be implementing breadth first search no matter what. Just find that shortest augmenting path. If we do this, then the shortest path by the number of nodes visited will always be increasing or staying the same. Every time we augment this, we're finding the shortest path, the shortest path, the shortest path. Well, now that's blocked off. The next shortest path, the next shortest path, etc. And if we do this process, we'll find that to do this, the maximum number of times that we'll be iterating is big O of V times E. Is there any intuition that people can think of as to why that is the case? If you're choosing, let's actually just go back real quick. Take a second and look at this line. And I'm going to go back to the last example. So it's obvious here that choosing the shortest path is the best answer. This will solve it in 2 iterations. We find the SUT path and then the SVT path, and each one subtracts 1 million or adds 1 million to the flow, and we never consider the edge between U and V. Is there any way we could modify this problem to make that more difficult for something strictly using breadth first search?
Number of edges spread out maybe or no. Breadth search does goes through all the edges later and later. The bottom to the top.
I know how we could make it harder for,
How could we do it?
we remove its ability to get to the destination.
Then it would terminate immediately.
Yeah, right idea, but no. Well, at least you have the right direction, maybe.
So as we do this, we're going to be finding the flow along the shortest path. That means that that path is no longer valid. The only way that the length could possibly stay the same is if we have an example like the last example where we have an edge that flips direction and then allows for flow in the opposite direction in the next iteration. Otherwise, this will be increasing every time, the actual length of the path, or staying the same if there's a second path that's exactly that many nodes that shares nothing in common. So eventually we're finding longer and longer and longer paths, but the shortest paths that we are in are the ones that we're very quickly going to go down. The only time this can be suboptimal is if there is a longer path that cuts off the shorter path's flow that we're continuing to consider, like in the prior example. So I like that example a lot for that idea. It's worth looking at this proof, I find, because it's just worth, it's not worth doing in class because it would take me the entire class to draw out and explain, but on your own, as you sit, read through it, try to understand it, it makes a lot of sense. So in each iteration of Ford Fulkerson, this is just for a single pass of Edmonds-Karp, takes big O of the number of edges time. So our total runtime for this process is VE squared in the worst case. And that becomes the new upper bound on the amount of time that it will take using breadth first search in order to solve this. Just to make sure that we have some experience with this, I have an example for us to solve. So this example is not using Edmonds carb and is not optimal, but we can at least see it working on Ford Fulkerson. And the way that I want to start this process is just looking at part A here. This is the original graph. Instead of picking the process that it shows, I want us to go through Edmonds carb. So what I'm going to do is I'm going to go through this and show Ford Fulkerson as it is, but then we'll come back tomorrow, I think, and do this for Edmonds carb as practice. So we just look for any augmenting path according to Ford Fulkerson. We're not using breadth first search here to find the shortest possible augmenting path, but we found an augmenting path. What is the bottleneck on this augmenting path?
Wow. The minimum value is 4. See? Ah,
Yeah, minimum value is 4, so that's the bottleneck. So when we convert this into its associated representation, we take every one of these and we fill 4 capacity along each one of those edges. So S to V1 gets 4 in that direction filled. 4 of 12 is filled from V1 to V3. 4 of the 9 is filled from V3 to V2. 4 of the 14 from V2 to V4, and 4 of the 4 from V4 to T.
okay.
So that is pass number 1. Now we go back to whatever algorithm is finding some simple path from source to sink. And in B, we find this path. What's the bottleneck on this path?
4.
It's also 4 between V2 and V1. So we're going to go through and add 4 flow in this along the S to V2 edge, 4 flow along the V2 to V1 edge, 4 flow from the V1 to V3 edge. Note that we're adding the existing flow. This was also an edge we considered here. So we're adding an additional 4 flow for a total of 8 flow. And then another from V3 to T, adding another 4 flow there. Is there another augmenting path at this point? Can we get from source to sink? We're referring to this right here. Is there a path from source to sink? Yes, there is. There are multiple paths still
Yeah,
from source to sink.
There are. I thought so.
So we can find more of them. Here's another. We can find yet another path. And the bottleneck here is again 4. So we're going to add 4 to each of these edges. And we find that this edge flips in direction again.
So, and then we basically go, let's see, S to V2, then V2 to V4. Not even V4 to V3.
From here, there's still another path. So we're going to find another path. This is the path that we find. So we're going to look at the bottleneck, which is 7 this time. We're going to add a 7 flow along this path. So we do that and we end up with the result. Is there a path from source to sink still?
I think there is, well, here's 1, 2.
There are a few left still. So there's more to look at.
Yeah, I thought so. So it's 8.
We'll find another one.
4 is the bottleneck this time again.
So we do that and we end up with this. From here, is there a path from source to sink?
No,
There is not. So we terminate, and this is the end flow network. Now, this took quite a few iterations to converge, even with a very small graph, because we were not following Edmund's cart. This was just Ford Fulkerson with random augmenting paths picked. So we have a couple of minutes to start, is take this network at the beginning and actually apply Edmund's cart. So what happens when we look for the shortest path by number of edges, not edge weights, and use that to update? In how many iterations do we converge? Go ahead and draw that out.
yeah.
Question.
Would it be,
You want to say 3 total?
Yeah,
so,
What's the first path?
you said at the very top, so you see.
Yeah, 16, 12, 20. Is there any path that's shorter than 3?
no,
No. There are multiple paths that are 3, so it doesn't matter which one we pick. It's perfectly fine to do this 16, this 12, and this 20. The bottleneck is the 12.
Yep.
So we're going to say there's 12 out of 16. This edge doesn't exist. It's pointing backwards now. With that 12, I guess we can keep the 12 there. And then we have 12 out of 20 in use. So this is a 12 going back, and I'm really just going to produce this as an 8 moving forward. And I'm going to say that this is a 4 moving forward and a 12 moving back. Okay, we can find another one that also is 3. We have the 13, the 14, and the 4.
4 is the bottleneck.
So 4 is the bottleneck there. Yep. So we're going to have now 9 moving forward and 4 moving back. We're going to have 10 moving forward and 4 moving back. And now just 4 moving back. Is there another augmenting path?
Yes.
Yes,
No.
there is.
Yeah.
We can go from S to V2. There's still a 9 edge there. A 10 edge from V2 to V4. A 7 edge from V4 to V3, and an 8 edge from V3 to our sink. So what is the total there? What's the bottleneck? It's the 7. So we're going to add 7 on the way back. That's still 2 on the way forward. 7 more. This is just 3 forward and 11 back. This is now completely in the opposite direction. This 8 becomes 15, and this 12, not 15, this 8 becomes 1, and this 12 becomes 19.
Happened to your fancy eraser.
It's too far away. I don't have enough time to get it. Is there an augmenting path now?
No.
No.
So they're like, that's like 3 or 4? No, that's 3 iterations.
Yeah. So how much flow is going through this network?
No.
How can we answer that? There are a couple different ways. A couple different easy ways. Yeah, it actually ends up, in any slice we can make in this graph. The sum of what's flowing backwards, or what arrows are going backwards is the flow. So we can make that cut right here. And we look at 19 plus 4, that's 23. We can make the cut right here, and we look at what's coming backwards, 12 plus 11, that's 23. If we make the cut literally anywhere else in our, it doesn't matter where we make that cut, in between vertices, the amount flowing back toward the source is going to be 23. Which is a very interesting component.
Okay, now I get it. I'm gonna have to practice.
Yeah.
Whoa, we're
We are out of time, so we're gonna come back tomorrow and kind of maybe some last minute thoughts on this before we dive into either the hardest or second hardest unit of the quarter. We finally reached the point where we're back to something very difficult. Sorry, but it's very important.
Yes, it's big, we have these quantum mechanic on here, right?
And be complete this theory.
I see it.
Wait, I'm sorry, what did you just say?
And be complete this theory.
And Jason's theory, that's not one I've heard before. I wasn't sure if I was hearing.
And produce deterministically polynomial.
Oh, great.
Sounds wonderful. Thank you for that.